This is a superconductor. It has zero electrical resistance. But is that really true? If I try to measure the resistance with my normal digital multimeter, you can see I just get zero. Now copper has low resistance, but it's not zero. You have to use something called the 4-point method. So I'm getting around 1.6 milliohms here. So a very low resistance, but this is a good conductor here. But now let's compare it to a superconductor. As you can see, it drops and then suddenly it plummets to zero. So we're getting literally zero resistance across the probes here. This means that the voltage drop across these two electrodes is zero. We're running a known current through it and applying Ohm's law, but since the voltage is zero, the resistance is literally zero. Okay, it's now superconducting. Now this 4-point method is nice because it means we aren't measuring the resistance of the wires that are taking the measurement or the contact resistance of those wires on the superconductor. So how is it possible for there to be zero resistance, not just low resistance, but literally zero? When electrons flow through a normal conductor, they sometimes bump into atoms in the positively charged lattice of metal atom. This causes the atoms to wiggle a little bit, which we know as heat. But something odd happens when you cool down the atoms enough. As the electrons flow through the lattice, they pull on the positively charged atoms around them. To a neighboring electron, this area now looks positively charged, so it's actually attracted to the region where the other electron is. This causes the electrons to move together in pairs called Cooper pairs. These pairs of electrons act as though they're bonded together. Now the physics of bonded electrons gets really interesting. Electrons are what we call fermions, which have a spin of 1/2. They obey the Pauli exclusion principle, which states that they can't be in the same quantum state at the same time in the same place. However, when two electrons bond together in a Cooper pair, one has a spin of up and the other has a spin of down. Combining together, it gives them a total spin of 0. This turns that pair into what's called a boson. Bosons, unlike fermions, don't obey the Pauli exclusion principle, so they no longer behave like individual point-like charged particles in the superconductor, but they act like one single wave in the superconductor now. And the electron wave has a larger wavelength than the spacing of the atoms in the superconductor. In this wave simulator, you can see that when we have a barrier that's on the same order of size as the wavelength, it scatters the wave. But when the wavelength is much bigger than the barrier, the wave just moves on undisturbed. This is what's happening in the superconductor. The energy to break up this wave is larger than the energy available in the atomic lattice. That means I can hook up my car battery to it like this, and it can pump as much as 600 amps through it, and it'll still remain a superconductor.